So welcome everybody to this session, invited speakers for the ICM. And it's my great pleasure to introduce as a speaker, Professor Mariusz Lemanczyk. And I just would like to say a few words about his sort of scientific trajectory. I mean, he received his PhD in 1981 from the Nicolaus Copernicus University in Torun. And then he moved to Warsaw, where he habilitated in 1991. And later on, he became and is at the moment professor at Torun. I mean, he received various prizes, but one of the very prestigious prizes is the Stefan Banach Prize of the Polish Academy of Sciences. His science is sort of many contributions to ergodic theory and dynamical systems, and I guess this will be also the topic of the talk which he's going to present right now, which is on Furstenberg disjointness, Ratner properties, and Sarnak's conjecture. So please go ahead.
Good afternoon. I would like to present an overview of Sarnak's conjecture, mainly from the ergodic theory point of view. So let me start with some basic definitions, notation, and some recallings. So the Mobius function is an arithmetic function which takes three values, 0, -1, and 1, and it is equal to -1 to the k if n is a product of k distinct primes and is 0 otherwise. If we are given a homeomorphism T of a compact metric space X, then Xt is called a topological dynamical system, and we say that this topological dynamical system is Mobius orthogonal if mu is orthogonal, or is uncorrelated if you prefer, is orthogonal to all continuous observables of our dynamical system. And finally, Sarnak's conjecture tells us that all zero entropy topological dynamical systems are Mobius orthogonal. We often say that the homomorphism T is Mobius orthogonal, or we say that the dynamical system Xt satisfies Sarnak's conjecture, which is maybe not completely correct, but at least is understandable. So an arithmetic bounded functions, all functions which appear here will be bounded, is called multiplicative if u of mn is equal to u of m times u of n, provided we take two numbers mn which are coprime. So it's easy to see that function mu and its square are multiplicative functions. Another function which will appear during this talk is the Liouville function. So the Liouville function takes values -1, 1, and it simply tells us whether a natural number n is multiplicatively odd or even. So in other words, we look at the number of prime factors, and it's plus or -1 depending on the parity of prime divisors. So of course, Liouville function is also multiplicative. In fact, it's even completely multiplicative. So this condition here, mn coprime, is irrelevant. And you can see that there is this basic relationship between Liouville and the Mobius function. And it will not be surprised if I tell you that if in Sarnak's conjecture we replace mu by the Liouville function, so in fact the two conjectures are equivalent. Many other classical arithmetic functions are multiplicative, and to see how large the class of multiplicative functions is, let's just realize that if we set any values on the powers of the primes, so this yields a multiplicative function. So let us pass now to motivations which are behind Sarnak's conjecture. I divided them into 3 parts. So let's say general motivations, and then some difficulties, and then genuine motivations. So let's just start with this general motivation. So we have, on one hand side, we have prime number theorem, which tells us that the number of the primes in the initial interval 1x is approximately x divided by log x. On the other hand, we have that the mean of the Mobius function is 0. So in other words, well, you may think that approximately in the initial interval 1x, we have the same number of multiplicatively odd and multiplicative even numbers, or just simply we want to say that we have this phenomenon of cancellations of plus and minus ones. So especially if you look at, so these 2 conditions are just equivalent. So of course, now if you look at this condition here, so you may see that this is nothing but Sarnak's conjecture in for the 1-point system, or in any dynamical system, we just consider constant functions different from 0. If you want to obtain Dirichlet's theorem from Sarnak's conjecture, so you just consider finite cyclic rotation systems. But anyway, if you see this kind of equivalence, so you can see that Sarnak's conjecture is a kind of good introduction to understand what can be prime number theorem in dynamical systems. But that's the next step of difficulty. I also mentioned that this prime number theorem can be read as cancellation of plus and minus ones for the Mobius function, for the Liouville function, just to see that this is completely non-trivial, and you shouldn't think that every second number is multiplicatively odd or multiplicatively even, whatever, because these cancellations of ones and minus ones is already Riemann hypothesis, and this says that if we have a certain speed of cancellation, so then in fact we encounter already Riemann hypothesis. So next thing is that natural question is that what makes Sarnak's conjecture a difficult problem, and let's just notice the following. So suppose that we have a measure theoretic dynamical system, that there are no assumptions on the entropy, and we look at the expressions which appear in Sarnak's conjecture, but from the point of view of L2 space. Okay, so then the spectral theorem tells us that this is the same. So the norm which we have here is the same as the L2 norm of the relevant trigonometric polynomial, which is, and the norm is computed with respect to the so-called spectral measure of the function f in this dynamical system. And then it turns out that then we know what the answer is, because there is an old result by Davenport, which tells us that if we look at this kind of expressions, so in fact they are uniformly bounded by this kind of expression. So if we divide by capital N here, you see that this is going to 0. So in other words, the L2 version of Mobius disjointness holds always for all dynamical systems. There is no entropy at all. In fact, if you use this Davenport estimate and you use the speed here, so you can obtain more. You can obtain that if you take any function, L1 function, then for almost all x's, you have this convergence to 0. Again, it is without entropy assumption. So this was already by Sarnak. We gave a different and simpler proof. The paper, joint paper with Alaoui, Wagner-Przymus, and Delary. So the answer to the original question, I mean, what makes it a difficult problem, is very simple. We want to see that this is going to 0 for all x's belonging to x. So now let us pass to the true motivation, which was for Sarnak motivation to study his conjecture. Namely, let's just recall Chawla conjecture. So Chawla conjecture is about autocorrelations of the Mobius function. You can see that we require here that all these autocorrelations, first of all, they do exist. They are equal to 0, unless we consider everywhere here even powers. For them, this is not always equal to 0. But for all other, we claim that this is equal to 0. So originally, Chawla conjecture was formulated for the real function. So it was in 1965. And of course, then you use everywhere powers are equal to 1, because lambda takes values +1, -1. There are also certain variations of Chawla conjecture and Sarnak's conjecture, and this was considered first by Tao. So you can consider logarithmic Chawla conjecture, which is, well, the same, but instead of Cesaro way of averaging, we use logarithmic way of averaging. So you have logarithmic Chawla conjecture, and you have also logarithmic Sarnak's conjecture, right? Here you give this logarithmic weights, and you normalize. Okay, so the basic relationship between Chawla and Sarnak's conjecture was given by Sarnak, and Chawla conjecture implies Sarnak's conjecture. The proof appeared, in fact, Sarnak's proof appeared on the blog of Tao a little bit later. It turned out that, in fact, this statement here, which we have, this claim here, Chawla conjecture is a purely ergodic theory statement, and it can be proved using ergodic theory. So this was done in the paper I already mentioned by Elad Delawi, Shimus Delawi, and myself. And well, Sarnak's conjecture is still open, but it has been proved in several cases. And let me just describe now two main strategies that lead to some results. So the first strategy is to look at these limits, I mean, the claim that these limits are equal to 0, just looking in the following way. We forget, so for the moment, just forget about mu n. So then what we see, these are just ergodic averages. And we just think that these are ergodic averages with weights, and the weights are multiplicative. So then the question is, okay, so we have to consider all possible continuous observables. So we have certain numerical sequences. So let's just try to abstract out, and we ask what assumptions should be made on a numerical sequence to obtain orthogonality to all multiplicative weights. So I have a sequence Fn, and I'm just asking when this limit is equal to 0 for each u, which is a bounded multiplicative function. So suppose that this has been solved, this problem has been solved. So then I have to go to my dynamical system, and I have to see what kind of properties should I have in my dynamical system to see that all continuous observables, they satisfy the assumption of this hypothetical lemma from number theory. And we will see that the answers are known. So on the number theory side, we have this DDKBSZ criterion. It will be formulated shortly. And on the ergodic theory side, we have Furstenberg disjointness from prime powers for measure theoretic systems arising from invariant measures of the homeomorphism T. So of course, this Furstenberg disjointness of prime powers it looks as a problem in ergodic theory, which is of independent interest, and in fact it is. But it was also a source of some controversies, because, of course, we see that Chawla conjecture implies Sarnak's conjecture. So if Sarnak is false, so then Chawla is false, and the problem is solved. But if we prove Sarnak, so then what? that's maybe not, it's not completely clear strategy how one to prove it. And okay, so this is the first strategy. So now let's try to see the other strategy, which is now to look at Sarnak's conjecture, but now we forget for the moment, we just forget about this ft and x, and we see that we have that the average of mu is equal to 0. So now I want to see, okay, so I have I have that certain average of a multiplicative function is equal to 0, and I want to see now that these averages, I give to these averages ergodic weights. Okay, so in fact I insist on looking on mu itself. So just to see, of course, this experiment does not look very symmetric, right? So let's first make it more symmetric, and let's just see that this mu n I can write also as a certain observable in a certain dynamical system. And what we write here is this function pi 0 computed at the orbit of mu. And what is the dynamical system which is behind that? Well, so that's the following construction. So we consider, let's say, mu as a two-sided sequence. Let's symmetrize it. For example, mu of minus n is equal to mu of n, mu of 0 equals 0. And then we consider the corresponding subshift, namely we take remaining in that space, we take the shift, left shift, so shifting sequences by one position to the left, and we look at the orbit, so that's a homomorphism, and we look at the orbit, and then we take the closure of the orbit, so we obtain the Mobius subshift. So now mu is a point in my dynamical system. So consider the corresponding empiric measures. So these are measures which look at the initial part of the orbit, and measure is purely atomic, and all points they have the same probability. So now the space of measures is compact, so we can pass to any subsequence that converges. And this gives me a measure-theoretic dynamical system, which is called the Furstenberg system. I will come back to that construction soon. Well, anyway, so we have this Furstenberg system. So now the idea is, okay, so I started with mu, I obtained a certain bunch of dynamical systems. So I try to find now special properties of these Furstenberg systems, which must be implied by arithmetic properties of the function mu. And what I want to see is that whichever Furstenberg system I take, I want to see that this function pi 0 is orthogonal to L2x nu space for any cohomogorov zero entropy system. So I take invariant measure in my topological system. I assume that the cohomogorov entropy is 0, and I have to consider now joinings between these two systems, and I want to see that pi 0 is orthogonal to the coordinate given by x. So Furstenberg disjoint is, of course, is welcome, but maybe it's too strong. But we just need this condition of orthogonality. Well, so for example, the most beautiful result, which is obtained using this strategy by Holst and Franzikinakis, which will be shown soon. So slightly simplifying the approach is that Furstenberg systems of the Mobius function are factors of dynamical systems given by strongly stationary processes. Okay, so let me just come back to this controversies. Let's first clear up the situation. So you remember that the controversies were that the Chowla conjecture implies Sarnak's conjecture, but not vice versa. So why should we care about proving Sarnak's conjecture? Well, so in 2016, maybe in 2015, Tao gave this breakthrough results Namely, he proved that logarithmic Chawla conjecture is equivalent to the logarithmic Sarnak's conjecture, and he also proved that logarithmic Chawla conjecture holds for autocorrelations of length 2. So if you take this, of course, you may still wonder, okay, so this is logarithmic Sarnak's conjecture and logarithmic Chawla, but what about the original Sarnak's conjecture? Well, then, based on this result, in fact, what we noticed a little bit later, so that's in a joint paper with Gomis and Delary, is that Sarnak's conjecture implies Chawla conjecture along a subsequence. In other words, there exists a universal subsequence Nk such that all these autocorrelations, they are really zero for all powers and for AIs as before, and all powers not all even. So if you think about this result, so let's say one can say what is the strategy of the proof. So if you have a Sarnak's conjecture, so if you have a logarithmic Sarnak's conjecture, then you have a logarithmic Chawla conjecture, but then somehow you play on a relationship between logarithmic and Pesaro averages, and you see some kind of convexity with that appears, and the fact that logarithmic Chawla conjecture holds is something that there exists a certain invariant measure which is ergodic, but ergodic measures are extremal point, and finally, you apply Milman theorem. Anyway, Tao extended this result, and he proved that if you have Sarnak's conjecture, so then in fact, so we have this Chawla conjecture along the subsequence, but the subsequence is of full logarithmic density. Okay, so now let us pass to description of, or maybe to present some main steps in applying this MW strategy. So if you think about the number theory side, so this is this WC, Delange, Catoy, Bourgain, Sarnak, Ziegler, criterion. And it tells you the following. Okay, so I'm interested to take an arithmetic sequence. And I would like to see that this sequence is orthogonal to any multiplicative, or to any bounded multiplicative function. So what should I know about this sequence? Well, so the criterion is that look at, so given this sequence Fn, you have many subsequences which are, you just restrict your sequence to subsequences given by arithmetic progressions. So here we take centered arithmetic progressions with difference, which are distinct prime numbers, and we want to see that the sequences which we obtain are pairwise orthogonal. So this implies that in fact the whole sequence is then orthogonal to all multiplicative weights. So in applications, so when we are given a dynamical system, so of course Fn is nothing but continuous observable in our system. So in other words, we have to study this kind of sums. So okay, so now we have to pass to the ergodic theory part of this strategy. So in other words, we are in this dynamical system Xt, and suppose that somehow we control the set of probability Borel T invariant measures, and also, let's say, for all powers. So for example, suppose that there is exactly one such measure, so that case is called a unique ergodic case. So recall also the basic fundamental definition in ergodic theory, which tells us that if we have two dynamical systems, so you can join these systems, so you can create a system which sees both of them, and in a sense is minimal, that's a minimal construction. So what we want to see, we consider all possible R1 cross R2 invariant measures on the product space Z1 cross Z2, and we assume that they have the same, they have the correct marginals. So we say that they are Furstenberg disjoint if the only way is the obvious way, namely just take the product measure. So now suppose that when we take this P and Q prime numbers, which are distinct, okay, so we have the same measure, the same system, but because we take different primes, so we have two different dynamical systems, or it may happen that they are Furstenberg disjoint. If so, then continue. What we are, okay, so we take the product system, and in this product system x cross x, we consider as a point v to x, and we study this kind of empiric measures. Because the space of measures is compact, so we can assume that this converges to a measure. But this measure has to be P cross TQ invariant. So we obtain a joining between these two systems. That is the idea. So once we have this, so when you decipher what this convergence of measures means, so then we find that this sum we are interested in, they converge to the integral of f tensor f against the measure rho, which is a joining. And if I know that this joining is just product measure, I know how to compute this integral, and we are done. Of course, I'm interested in the case where I find 0. And using this method, many results have been proved. I will not read names, sorry, but you can see this is only a sample of results. Well, so Sarnak's conjecture has been proved for dynamical systems of algebraic origin. So this was at the very beginning, in fact, of Sarnak's conjecture. And then, so this is more recently, so this was a question by Marina Ratner, what happens if, for example, we take horocycle flows, you change time for horocycle flows, do we obtain also Sarnak's conjecture? So this was answered recently positively, so in the paper by Kanigowski, Ulcigray, and myself, and also by Flaminia Forni. Another question which somehow originated with a paper by Jean Bourguin, so it was about interval exchange maps and another classical class of measure preserving systems. So the question was whether almost all interval exchange maps they are Mobius orthogonal. So the answer is also yes. So this is also recent. So this is in joint paper Kanigowski and Radziwiłł and myself, but there were some predecessors. And you can see that there are many results. So for intervals, for exchange of 3 intervals, this was done by Chaika and Eskin. Then you have special, so that's a class which is of special interest, namely the class special distal systems, so-called Anzai-Skew products. Finally, Wong in 2015 proved that for all analytic Anzai-Skew products, we have the validity of Sarnak's conjecture. Then there are many papers where some dynamical systems of number theoretic origin were considered, and Sarnak's conjecture was proved. Maybe the most known result here is that for all automatic sequences, we have Mobius orthogonality. It should be also added that many results which are using this technique, this DKBSZ criterion, they were using also a breakthrough result from 2015 by Matomeki and Radziwiłł, which was done in number theory and which answered the question on a short interval behavior of good multiplicative functions. Okay, so let me now be a little bit more concrete about Furstenberg systems of a sequence. And let's just go through some basic facts once more. So given a compact metric space, so where we consider the space of probabilistic Borel measures, so that's a compact space in the Veech star topology. So in that space, we have the natural, if a homomorphism T is given of that space, so then we have the space of T invariant measures. and this convex, if you look at the extremal points of this set, of this convex set, so you obtain exactly ergodic measures. So this this construction of this kind of remark we have already seen, namely if we have a point little x in X, so then we can create empiric measures, and any subsequence that converges gives me a measure which is the invariant. So, okay, so then the basic definition of point X is called generic for a measure if the whole sequence of empiric measures converges and the limit is just this mu. So in other words, but this is somehow recalling the definition of weak star topology, we see that these ergodic averages, they converge to the integral. If the convergence takes place only along a subsequence, okay, so then we say that X is quasi-generic. And of course, because of compactness, each point is quasi-generic. Then given little x, we can consider all measures for which x is quasi-generic. So this is this V of x, and that's a set of visible measures from the point x. We can repeat all these definitions in the context of logarithmic averaging. So we consider now logarithmic empiric measures and their limits, and we obtain visible measures from the logarithmic point of view. And if you look at these sets of visible measures, both from Cesaro point of view or logarithmic point of view, you obtain the following: that either point is generic, so then of course this set has cardinality 1, or it has to be uncountable because it is connected. So coming back to the situation which we have already encountered, so if we have a compact subset, think about a finite subset of the unit disk, and we have a point and we have a sequence, the two-sided sequence. So then of course we can consider this point as a point in the subshift which is generated by this sequence, and we can think about the measures for which this point is quasi-generic. So the definition, this fundamental definition here, is that given a sequence, a two-sided sequence by a Furstenberg system of it, we mean any measure-theoretic system XU kappa S, where kappa is visible from U. And of course, logarithmic Furstenberg systems are defined similarly. So now we can come back to Chawla and Sarnak's conjecture. So namely, we just noticed that, okay, so now I rewrote here Chawla conjecture for the Liouville function, and it turns out that this really holds if and only if lambda is a generic point for the Bernoulli measure 1/2 in the subshift, in the shift -1, 1 to the z. For the Mobius function, it's a little bit more difficult to give the dynamical meaning of Chawla conjecture. And for that, we have to first recall that it is classical that if you take the characteristic function of the set of square free numbers, so in other words, if you take mu square, so this point is generic for a measure. In fact, it's a zero entropy measure. Nowadays it's called the Mirsky measure. So this is notation for this measure, and this measure is supported on the subshift of square free numbers. So these are 0, 1 sequences. So Chawla conjecture for mu is equivalent to the following: that mu is again a generic point, but it's a generic point for the relatively Bernoulli measure, which is on that then the shift on these three symbols -1, 0, and 1. And it has to be relatively Bernoulli over the Mirsky measure, which is given by mu squared. So in other words, so if you want to imagine this measure is simply that you have this 0, 1 sequences, and now well, above what you see, these are sequences of zeros, ones, and minus ones. And if you have a 0-1 sequence, so with equal probability, 1 is changed into +1 or -1. Okay, so let's now pass to maybe the most famous result, which was obtained using this strategy EW. Namely, that's a theorem by Franzikinakis and Holst from 2017, and it says that logarithmic Sarnak's conjecture holds for all deterministic systems XT, for which the set of ergodic measures is countable. So in particular, logarithmic Sarnak's conjecture holds for all uniquely ergodic systems of zero entropy. So it's a long and deep paper, and the only thing I would like to say here is that they studied Furstenberg systems of the real function, of the Mobius function, and they proved that these systems are factors of systems without irrational eigenvalues, and what the most important part, and whose ergodic components are of the form Bernoulli times nil automorphism. In fact, well, slightly simplifying is that they proved that this is somehow related to the theory of strongly stationary processes. Okay, so it turns out that this logarithmic Sarnak's conjecture, we can find some equivalent reformulations which reduce the number of systems we should consider, because we should consider all deterministic dynamical systems. So let me just give you two results here. So if XD is a compact metric space, so in this compact metric space, we introduce new dynamical all equivalent metrics, namely this mean metric Dn is just computing the following quantities. So we look at the piece of orbits, we look and then we look at the distances between t to the ix, t to the iy, and then we take the average. And then the dynamical system xt is said to have polynomial mean complexity if there exists a constant c, such that if you look at this limit inferior, you obtain 0. So what do we see in the numerator? Well, in the numerator, so given n, we have this metric dn, and we compute what is the minimal number of balls covering the whole space. And we want to see that this is equal to 0, and then Huang, Xu, and Ye, they proved recently that the logarithmic Sarnak's conjecture holds if and only if it holds for all systems with polynomial mean complexity. In fact, you can consider only subshift, and in fact, you can consider only subshifts with on two symbols. This is still equivalent. So to formulate another result, so I already used nil systems, but so let me just recall what we mean by that. So we consider nilpotent groups and lattices, so discrete compact subgroups, and then we have the natural actions on the quotient spaces, namely rotations. So these are called nil rotations. Nil system is something more complicated because, well, we just fix the degree of nilpotency, and then we should consider inverse limits of such automorphisms. But I will not go into details here. So the theorem which we proved recently is that, so that's the theorem with Kanigowski, Kouagoczymus, and de la Rue. We proved that logarithmic Sarnak's conjecture holds if and only if it holds for all systems whose all ergodic invariant measures yield nil systems. So of course, it looks as if there are connections between these two theorems, because Kanigowski, Veech, and they proved that all zero entropy homogeneous systems, they have polynomial mean complexity, but this theorem here is more complete. It doesn't see this algebraic structure. It only tells us something up to measure theoretic isomorphism. So it's hard to see what are possible relationships between these two these two theorems. Okay, but this was described some progress about logarithmic Sarnak's conjecture, but what about the original Sarnak's conjecture? So you may see that there is a basic difference between Chowla conjecture and Sarnak's conjecture. Namely, Chowla conjecture is defined combinatorially, right? This was the original formulation, but then we realized that it has a nice, simple ergodic theory reformulation. But what about the original Sarnak's conjecture? I mean, it has only its dynamical formulation. Is there any combinatorial reformulation of it? So do we have a combinatorial condition, internal condition on mu, which is equivalent to Sarnak's conjecture? So from the dynamical point of view, it was already speculated. It was speculated really even 10 years ago that the difference between Chawla and Sarnak's conjectures, it's the same as the difference between the Bernoulli property and the Kolmogorov property in ergodic theory. Kolmogorov property is so-called completely positive entropy condition, but it was never phrased exactly what do we mean until it turned out that in fact it was a formal conjecture which was phrased in 2016, and you can find this conjecture in lecture notes of Bill Veech. So let me just recall Veech's conjecture. So Veech considered the following situation. So he was considering Furstenberg systems of mu, and then each Furstenberg system gives me a stationary process, which is given by projections on coordinates. So in particular, we have this function pi0, which has appeared several times, which is looking at the zero coordinate. And his conjecture was that Sarnak's conjecture holds if and only if for each Furstenberg system, we have that pi0 is orthogonal to L2 of the sigma algebra pi of kappa. So what is this sigma algebra pi of kappa? Pi of kappa is the largest as invariant sigma algebra, giving a factor with zero entropy. So this is precisely, I mean, in this context, it's precisely the tail sigma algebra of our system. Okay, so, but this was a conjecture, and a result which we proved very recently with Kanigowski, Kawagachimus, and Delary is that the Veech conjecture holds. So you may wonder, what does it give us? Does it give us a combinatorial condition, mu, which is equivalent to Sarnak's conjecture? The answer turns out to be yes, because that's, you know, in ergodic theory, we have this K property, Kolmogorov property, and this is equivalent to K mixing. And fortunately, this K mixing can be localized, so can be also considered for a single function. And once you know that, you realize that this is true. So then you can write the condition of being orthogonal to L2 of the Pinsker using blocks and convergences. So you see this condition here. And to write this condition, I assumed that mu is generic, just to make the notation simpler. And I will explain to you what this condition means. So we take a block which appears on our Mobius function. So now I look at the position. At all positions, this block appears. So I obtain a certain sequence n1, n2, etc. So I see the same block. So if I look at this position, the initial position of the block C, so of course I see the same symbol, so nothing interesting happens. But now the whole set of return times I can shift. So we shift it, and what we claim is that when we read this position. So we see the cancellation phenomenon of plus ones and minus ones when n becomes larger and larger. Thank you. Bye.
So thank you, Mariusz, for a very
Thank
interesting
you.
and beautiful talk. I mean, so also in terms of the participants, which we, cannot see, but I mean, nevertheless, I would like to thank you for a very nice talk. Have a very good day.
Thank you very much, and thank you everybody for watching. Bye.
Bye.